I think it's time to get started. Welcome back, everyone. I hope you all had a good break. I had a good break, and I'm glad to be with you all again. Um, we have two more ordinary weeks, so we're gonna have homework due tomorrow, and also one more assignment next week, and then actually we'll have one more assignment that's due like at the final exam time, just to fill in the last few bits of stuff that we do. And everybody's talking about the old pass-fail. I know there's this new pass-fail option, although I think probably none of you can do it. It's not allowed for courses in your major above the 2000 level, which I believe you're all math majors or double, math computer science. If you're not, what are you doing in this class?
For fun.
For fun? Yeah, I don't know. Does anyone take this class for fun? I don't know. I think it's fun, but yeah, that's because I'm getting paid. Yeah, so but you guys, I mean, your grades are fine. If you're wondering about your grade in particular, let me know, and I'd be happy to tell you what your grade is so far. It's not so hard for you to figure it out yourself, but I'm happy to tell you also. All right, any logistical questions about the last 2 weeks or so? No, it's going to be great. So we are talking about sequences of functions. I said just a little bit about it last time. Sequences of functions. We're going to talk in more detail about it this time. I just gave you a little taste last time to give you the general impression. Sequences of functions and what like a sequence of functions converges to can be kind of weird. So one of the examples I said last time was something like this: fn of x equals x squared over n. This sequence of functions looks like it begins with x squared, which is a nice parabola. This is x squared, and then the next one, this is f1, right? X squared, and then f2 will be x squared over 2, which is sort of similar, but all the y values are cut in half. That's f2, and then f3 would be, like this. f4 would be like this, etc., right? And in this case, it seems like fn of x as a sequence of functions, it converges to f where f of x equals 0, the 0 function, right? Because these guys, as the n increases, these functions, they just keep on kind of flattening out more and more. That was f4. f5 would be similar. They're all parabolas, but they are flatty as you increase the n. All right, so it certainly seems like fn of x approaches 0 here. Even though, I mean, they are flatty, they become flatter when you're looking at them just like from this viewpoint. But it's still the case that every one of these functions is unbounded, right? No matter how flat it is here, eventually this is still a parabola and will still go up to infinity eventually as you go out to the two sides. So it's a little strange that they converge to 0 even though they're every one of those functions is unbounded. These are some weird things we're going to talk about. Here's another weird example. That one I just said I mentioned that example last time. Here's another even stranger one. How about f of x equals e to the nx? All right, e to the nx. So the sequence of functions is, e to the x is the first one, e to the 2x, e to the 3x, etc. This is the sequence of functions. I would like to know what they converge to, if anything. Just if you don't know what's going on, it's helpful to try and look at these things on a graph. So the graph of e to the x looks like this. E to the x looks like that. All right, it's an exponential growth, so this goes, quite steep eventually, and it goes through 1, right? That's because e to the power 0 equals 1. And then as you go off to the left, it approaches 0. What about e to the 2x? Maybe I'll draw e to the 2x in red. E to the 2x, as you go to the right, it increases even faster than e to the x, but it still goes through 1, because when you plug in 0, you get e to the 2 times 0, which is still e to the 0, which is still 1. So it looks like this, even steeper over here, e to the 2x. And on the left side, I don't know if you've ever looked carefully at a graph of e to the x, it does that on the left side. It goes to 0 sort of even faster. All right. What does e to the 3x look like? It looks similar. So it looks like this, and then increases even faster over there. All right. E to the 4x, I think you get the idea, right? I'm just going through all my colors here. E to the 4x, like that. And so on. That's really mighty close to the y-axis, isn't it? This is what this sequence of functions looks like. All right. So, what does it converge to? Well, perhaps the answer is it doesn't really converge to anything. Although, I would say in this example, it does converge to something for some values of x, and it seems like it doesn't converge for other values of x. Maybe can someone shout out, do you see for certain values of x somewhere where it does converge? Like, for which values of x would you say it does converge to something?
It looks like it's converging to 0 for the numbers less than or equal to, or less than 0.
Yeah, on the left side, it looks like the y values are going to 0. So I would say it seems like when x is less than 0, fn of x converges to 0, right? As a sequence. I agree. Okay, what about when x is greater than 0? I don't think it converges to anything. As you increase the n, it's just going to get increasingly steep. What about when x equals 0? Actually, when x equals 0, you can see all of these functions equal 1. So when x equals 0, it does converge in that case. Fn of x converges to 1. In fact, it always equals 1 as a sequence. This is a constant sequence, 1, 1, 1, 1, 1, right? When x equals 0. So in this example, in terms of a function which this converges to, I would say, I'm going to try and keep that picture on the screen. On all of R, this sequence of functions, Fn diverges. That is, it doesn't converge to a single function that works for all real numbers, right? But if I only consider the left end, so on this, minus infinity to 0, including 0, then it does converge. Fn converges to 0 when the values are to the left of 0, and 1 when the value equals 0. So I will write that as a piecewise thing. F of x equals, in two pieces, 0 if x is less than 0, 1 if x equals 0, right? If you consider on all of R as the domain, then Fn diverges. But using the domain only of minus infinity to 0, then it does converge to this weird function in two pieces, this discontinuous function. All right. So the moral of this story is when we take the limit, when we look at the limit of a sequence of functions, this is a strange thing. The domain might be different. Like these functions, they all have, I meant to say Fn of x, right, is e to the nx. They all have domain being all real numbers, right? The thing they converge to, though, it's it cannot be defined for all real numbers. Its domain is only the negative one. So when we look at a limit of a sequence of functions, the domain may change, and in fact, it might shrink. Like the domain now, and once I take the limit, the domain became smaller than just all real numbers. Now it's only the left side, right? The negatives or 0. The domain may shrink. It's actually not possible to converge to something with a larger domain. That wouldn't really make sense. But sometimes it converges to something with a smaller domain. So the domain may shrink. Strange but true. And also, you can see in this example, the limit may not be continuous anymore. Even if all the things that you started with were continuous, the thing they converge to might not be continuous. This is such an example. All right. So far, everything has been somewhat informal, but I think we should get down to the real business of talking about what exactly does it mean when I say a limit of a sequence of functions. I never really gave a definition for that. It's not so difficult though. But here's some real talk now about the limits of a sequence of functions. So here's the definition. It's actually two slightly different types of limits of sequences of functions that we're going to talk about. And the first one is called the pointwise limit. So I'm going to say let Fn goes from some set A to R. I don't write things this way very often, but I hope this looks familiar. When I write this, it means that Fn is a function, and this is the domain, and this is the codomain. See, when you're talking about this, it's important to we need to allow our functions not to be defined on all of R sometimes, because you can see in that example, for instance, sometimes you have to end up with something whose domain is not all of R. So we're going to talk about the domain set is just some set A. So Fn is, they all have the same domain though in the sequence. Let this be functions for all n in the natural numbers. That is to say, I have a sequence of functions. And then we say Fn converges pointwise to f of x, some other function. Sorry, can I squeeze in another word there? Sorry about that. Pointwise on A. It matters what set you're talking about. That was in the previous example, we saw that too. It converges pointwise on A to some other function, f of x, when we don't even need the epsilons or anything here. It's easy enough to just say for all A in the set A, we have Fn of A converges to f of A. All right. Pointwise convergence means that for every individual point in the domain, this sequence converges to f of A. And when I write this convergence here is just convergence of an ordinary sequence of numbers. Once you plug the A in here, what you have is just a sequence of individual numbers. And I'm just saying these individual numbers, they converge to this individual number. All right. This is what it means for a sequence of functions to converge pointwise on a particular set. Let's do an example. Are there any questions about that at this point? No. Let's do an example. How about, this is an example. Whoa. All right. Fn of x equals sine of x over n. I'd like to know what does it converge to, and then let's see if we can actually demonstrate that. And on which set does it converge, right? Like in this example up here, we had to kind of look at the picture to decide the set on which it converges is the stuff to the left. It does not converge on the set to the right. How about this? Let's see if we can decide what is it converge to, and on what set does it converge if any. Sine of x over n. Let's see if we can draw the graphs, just because if you don't know what else to do, you might as well just see what the graphs look like. I suppose this is easy if you have a computer or something, although this one in particular is not so bad. f1 of x is sine of x, so everybody knows what that looks like. f2 is sine of x over 2, right? Then we get sine of x over 3, and so on. So on a graph, I'm going to try and plot these all together like I did before. Sine of x, everybody knows, looks like this, right? And continues. Where this right here is 2 pi. I'm using radians, of course, because I'm a sophisticated adult mathematician. What about sine of x over 2? Can anybody say what does that look like when I draw it next to this one on the same graph? Is it shifted around, moved up, stretched around? Anyone remember? There was some, I'm sure you learned about this at some point in your youth. When I divide the x by 2 in there, what is the effect on the picture?
And it stretches.
Yes, it stretches. Would you say it is a horizontal stretch or a vertical stretch?
Horizontal.
Yeah, so the way you want to think about this is here, that when I change from x to x over 2, I am stretching the x values. Now, you should wonder, because all I did was I changed x to x over 2, right? When I divide in the x, when I divide on the inside of the function, that causes the x values on the graph to expand out. It's because you're dividing by 2 before you plug it in. What I'm going to see over here, for x over 2, I'll do this one in red. It's going to do the same thing, only it will be stretched out by a factor of 2. So instead of sort of one full cycle in that 2 pi interval, it goes like this, and then continues like that. All right, this is what this is f2. All right, and if you don't believe me, you can just think about like what would happen if you plugged in right here. If you plugged in x equal pi over 2, you divide by 2 first, so you get whatever you would have got by plugging in x equal pi to the original function. So it's 0. All right, what about, say, this one here? I'll do in blue. This will be stretched out by a factor of 3, so it'll go out sort of even further, like that, right? And so on. The next one, if I did sine of x over 4, f4, it gets stretched out again even further, right? Every time, next one of these, stretch the graph out even further. What do you think? Does this converge to anything? Now we're talking about converges pointwise. So the proper way to think about this is, remember the definition says, at each individual point, here for all x in the domain, we have this convergence. So you want to think about, if I just focus on a single point, let's say like this point right here, let's imagine that's my point A. Do the y values actually converge to anything? Well, in the first case, this was the y value. Then the second one, this was the y value. Then this, then this. Do those y values converge to anything if I keep on going up in the sequence? Yeah, I think in this case, fn of a actually will converge to 0, because I'm going to get like these values. I mean, it's hard to say exactly what they are, but they are going to get smaller every time, because they result in stretching the sign out even further every time. All right, so that's true of this point that I drew right there. Is it also true of other points? I think it is. It's less obvious, but even for this point over here, now these lines, they look like they're kind of all over the place, but you should feel like eventually, if you go down far enough, like this same kind of behavior that you see over here, eventually these lines will be stretched so far out that they end up like all the way over here, right? And even around this point, the value will still go to 0. All right, this is your idea. So anyway, all of that, looking at the picture, is just to give you an idea. So I'm going to say at this point, looks like fn of x converges to 0 on what is the set on which it converges? I think this is going to happen for every point. It will always converge to 0. So I'm going to say on R, and I should say pointwise. It looks like this sequence of functions, pointwise, it converges to 0 on all of R. That is, this convergence happens at every point in the real numbers. There's not like some region on which it does converge, some other it doesn't. No, it seems to occur always. All right. Let's see if we can actually prove this. Actually, this is fairly easy to demonstrate. Once you have the idea in your head of what happens, it's not so hard to see why. In this case, so let's, I guess I'll write this as a little proof. It's not, it hardly deserves the name proof. What we have to show is this, right? For all A in A, we have fn of A converges to f of A. So what I need to show is, I want to show for all A real numbers, fn of A converges to, now what the definition says here is f of A, where f is the thing it converges to. Now in this case, my f is just 0. This is like the function f of x equals 0, right? So when you're showing that some sequence of functions converges to f, you would say fn of A converges to f of A. But in this example, what I said they're converging to is 0, so you put 0 here, all right? This is what I need to prove. Now, I would do this by saying let A be a real number. Then let's just write out what is fn of A. Well, it's sine of A over n, right? And can anybody say what happens to this? Like just looking at the formula, I think you can tell. What happens here when n goes to infinity? I'm trying to see what this converges to. When n goes to infinity?
0.
0. Why is it 0?
Sorry. Yeah, so when n goes to infinity, A over n will be 0.
Yes.
Goes to 0.
Right. So this really, I would say, in 2 steps. This goes to sine of 0 because when the n goes to infinity, the A over n goes to 0. And then what is the sine of 0? It is 0, right? Because it is. You learned it in high school or whenever you learned that, right? The sine of 0 is 0. Let me just comment, like right here. Is anybody nervous about this? Is it legal for me to, I'm saying the limit of sine of A over n, and I did the limit inside the sine. Is it legal to do the limit inside of one function? The answer is yes, it is legal because sine is continuous. Remember, when a function is continuous, it means that the limit of, if I have these things and they approach 0, then the limit of the function approaches the limit of, you know, f of 0 or whatever. So this little step here is valid. This works since sine is continuous. If that was a discontinuous function, then you're not allowed to just plug limits in on the inside of the function. But when your function is continuous, you are allowed to just sort of plug the limit on the inside of the function. All right, anyway, that's it. I mean, remember I said the proof was going to be very simple. So, you know, fn of A approaches 0 as desired, right? So it does pointwise converge to 0. Oh no, I lost my screen. That's all right, I know what to do. I bent down and I think I knocked the wire. It's coming. It's coming back. Yes, all right. Sorry about that. Okay. This was an example where it does converge pointwise. Any questions about that example? A little strange. I don't know. Is it strange? Can we revisit the one that I did at the very beginning? Fn of x equals e to the nx. I said a lot of sort of informal things, and I hope that what I was saying made sense, but we didn't actually demonstrate in detail any of these things. Let's see if we can do it. So I want to show that this is like a nice little homework problem. Let's show that Fn converges to F on this set. Pointwise, I always forget to say that. On minus infinity to 0 closed interval, where f of x is the thing that it converged to was 0 if x is less than 0 and 1 if x equals 0. All right, this is what I want to demonstrate. This was that first example that we had. If I just give you a sequence of functions, it's usually a good idea to look at graphs to try and first of all figure out what you think it converges to, and then see if you can actually prove it. All right, I want to show that it converges pointwise on this set, minus infinity to 0. Okay, let's do it. So just like before, this involves you have to choose some particular point in the domain, and then you do some simple business, hopefully simple business. So I'm going to say choose any A in, now the set that I'm talking about here is that one. It's not all of R, it's this set. The interval minus infinity to 0. And then what I want to show is that Fn of A converges to F of A, right? This is what we have to demonstrate. And this involves just sort of plugging into the formulas for the various F's and checking it out. Hopefully it'll work. Now, in this case, we are going to divide this into two cases. According to this formula right here, the 0 and the 1, you will see the values, the values of this function behave totally differently if the number is negative versus if the number equals 0. So, and there's those two cases exist here. So I'm going to say two cases. First of all, if A is less than 0, and then the other case will be if A equals 0, because it behaves differently. The F has a different value each time. All right. So in the case when A is less than 0, in this case, I want to show Fn of A converges to F of A, but F of A is 0, right? Because the definition of F is right here. And if the A is negative, then the F is 0, all right? So this means, can I just say i.e.? I want to show, I'm just plugging into all the formulas. Fn of A will be e to the n A, and I want to show that converges to 0. All right. And this, I mean, I suppose in the worst case you would have to use the epsilons, but in this case we can do this without getting so hung up on the epsilons. E to the NA goes to 0. This, this is like e to the x, right? But I'm talking about it on the left side. How do you know that it actually goes to 0 on the left side there? I think the easiest way to make this work is to write this. Oops. I'm not going to use any special properties of e because that's too fancy. I don't want to get into that. This is equal to that, right? E to the NA is the same as e to the A to the power n. And this, e to the power A, I can just say this goes to 0. Since e to the power A is less than 1, and this is since A is less than 0, right? A is negative, so this is a negative exponent, so e to the power A looks like 1 over e to something. and that's going to be less than 1. And what that means is when I take these powers here, these exponents are going to go to 0, or these powers of e to the a are going to go to 0, because e to the a is like a fraction, right? It's less than 1. And so when you multiply it by itself over and over again, which is what this means, nth power, you're going to get things closer and closer to 0. All right. And this is the end of this case. So Fn of a converges to f of a as desired. All right, that's this case. The case when a is less than 0. What about the case when a equals 0? That's the other case, because when a is in this set, those are the two options, right? Less than 0 or equals 0. The other case, if a equals 0, well, in that case, what I want to show is Fn of, I don't even need to write a anymore, right? It's just 0. Fn of 0 converges to f of 0. Usually I put a, but this whole case that I'm talking about, the second case, is when a is 0, so I use 0. This, can I rewrite that? This means Fn of 0 would be e to the n times 0 goes to f of 0, and if you look at the definition of f up here, is here, f of 0 is 1. So I put 1 down here. All right. Is it true that e to the n times 0 converges to 1? Yes, because e to the n times 0 actually equals 1. So I can say, but e to the n times 0 actually equals 1 for all n. So certainly it is true, e to the n times 0 converges to 1. All right, because they're actually all equal to 1. And that's all it is. All right, we've demonstrated that those functions do converge pointwise to this weird piecewise f. Any thoughts about that? Questions or concerns? All right. All right. So this is a weird example in that, and I mentioned this before, but I just want to say, note, Fn are all continuous, and Fn converges to f pointwise on this set, minus infinity to 0, but f is not continuous on minus infinity to 0. So it is possible that you have continuous things and what they converge to is not continuous, even on the same domain. This is regarded as kind of weird and undesirable. In fact, if you look sort of closely about why exactly did that happen, I would say, if I was trying to explain that particular case, in the context of this example, if this is where the 1 is, say, and the functions, only just looking on the left side, the functions, they kind of looked like this, right? I'll do one more in black again. If you look at these functions, you will notice they get super steep right around this point here, right? They do converge, but these, I'll say it this way, the slopes get super steep, super duper steep even. Can you believe that? The slopes get super steep as you sort of go down, as you increase the n as you're looking at the sequence of functions. This should suggest to you, maybe you'll believe me when I say that this sort of issue is related to what we talked about individual functions, about uniform continuity. Remember we talked about how there was like a fancier type of continuity, uniform continuity, and there are like better theorems when you use uniform continuity instead of ordinary continuity. A function is uniformly continuous on a particular domain, means the slopes are kind of under control. And in this example, each individual function fn has a slope which is like finite or whatever. But when you increase the n, the slopes increase without bound, and that causes weird things to happen in the limit. And it's because of some lack of uniformity in the slopes as you go down the sequence. So I keep on saying there's another kind of convergence. There's pointwise, which we've been talking about all along, and then there's another kind which is called uniform continuous. And the idea behind this one is it is meant to disallow this kind of situation where the slopes go crazy. Now the definition doesn't actually mention the slope, but the point of the definition is to disallow that kind of behavior. So here is the definition of uniform convergence of functions. So it says, we say that a sequence of functions fn converges uniformly on some domain A to some other function f of x when, now do you remember, I don't know if you do, the definitions of continuity versus uniform continuity? It had to do with a very small technical change in the definition about the delta and the epsilon. In continuity, ordinary continuity, means that for every point and for any epsilon you can find some delta such that blah blah blah, whatever. Whereas uniform continuity means for every epsilon there is a delta that works at every point. That's the difference, is that uniform continuity involves the same delta works for every other point. And uniform convergence of functions is a similar thing. So we say the set of the sequence of functions converges uniformly on A when, unfortunately, I do have to write the epsilon stuff for this definition because you can't get there without writing the epsilon stuff. When, for all epsilon greater than 0, there exists. Now this is going to look like the definition of a sequence converging. We haven't done this in a while, but I'm sure you have fond memories. The sequence converging is not epsilon and delta, but it's epsilon and the big N, the natural number. For all epsilon greater than 0, there exists a natural number n, such that n greater than n implies fn of x minus f of x less than epsilon for all x in the domain A. All right. This is the definition of uniform convergence. And the important thing really is right here. This says that the same n works for every x value. The same n works for every value of x. All right. This is analogous to when we had the definition of uniformly continuous. So the same delta works for every like c value is what we said in that context. Uniform convergence of a sequence of functions means the same n value works for every x value. All right. So of the examples we've talked about, some of them converge uniformly, some of them do not. Actually, of the ones, and we can go through, we're going to go through some of them in detail. Of the ones we've talked about, actually none of them converge uniformly. Those convergences were all non-uniform. But I want to do an example which does converge uniformly. Let's try. So this is a, nice little homework question. Fn of x equals 1 over nx. So these functions, they all look like 1 over x, but they are dividing by that constant, makes it so that like the first one is 1 over x. The next one is 1 over 2x, which just sort of additionally divides everything by 2, and then divides everything by 3, and then divide by 4, and so on. They just get increasingly kind of steeper or like closer to the axes or something. I'm just drawing the right hand side. Of course, the other side does a similar thing. I'm going to say this converges uniformly. This is the other type of convergence on. Now, you can't actually say on all of R because all of R is not even the domain. Like 0 is not part of the domain. You have to choose some specific domain. I'm going to choose the domain just from 1 to infinity, right? Only considering these points. You could actually use any starting value you want, but you can't start from 0. You got to start from somewhere else. So you might as well start from 1. All right. I want to show that this converges uniformly on there to, what do you think the function converges to?
0.
Yeah, I hope you agree. Like if you're looking over here, these graphs, they are tending towards 0, aren't they? I think so. So I'll just write for clarity. 0 by 0, what she meant was the constant function f of x equals 0. All right. Converges uniformly. Okay, let's see if we can do the proof. We don't have to think too hard about it at the beginning. I mean, it is one of these like epsilons and n's proofs, which are, those are kind of intimidating at the beginning of the course. But now that we've been doing these all semester long, I hope you feel like you can at least set up the structure of such a proof, right? I'm going to say, let epsilon greater than 0 be given. And then what do we got to do? We'll find this big N such that if n greater than n, we have what we want is fn of x minus f of x less than epsilon. Well, I should actually plug the stuff in. Sorry, I meant to write. What is fn of x? It is 1 over nx. This is what you would typically do to start such a proof. Minus f of x is just 0, right? And I want to make that less than epsilon. And this has to be true for all x in my domain that I'm talking about, right? Remember that thing I said in blue. This must be true for every x. Okay, let's see if we can do it. As usual, I'll sort of do my work on the side, and I always do in blue. Absolute value 1 over nx. I don't care about the minus 0, right? And in fact, since x is from 1 to infinity, I also don't really care about the absolute values, right? This is just already equal to 1 over nx. All right. I would like to remember what you try to do when you're doing these proofs involving sequences is you want to try to somehow kind of solve that for n. And I especially don't like the x in there. I want to just see n here, or maybe end up with something like 3n, and then I can say let epsilon be n over 3, or let the big N be epsilon over 3, something like that. So you should be thinking about how can I get rid of the x, and of course I can use equal or I can use less than or equals. And in this example, you can just do this. You can just throw the x away. Why is that? It's because x is in this set, 1 to infinity, which means what I see here, 1 over nx, is smaller than just 1 over n, like 1 over n, right? Because I'm multiplying by some number that's bigger than 1. If you want to be a little more explicit, you could say it that way. I don't mind getting explicit sometimes. X is bigger than 1. And so this fraction here is less than this fraction here. But of course this is 1 over n, right? So I will say, this is how we finish those proofs involving sequences. I need 1 over n to be less than epsilon, i.e. epsilon to be, no, n to be greater than 1 over epsilon, right? I know we haven't done these sequences in a long time, but this is a very standard thing. You may have to refresh your memory when you're doing the homeworks. Very standard way to do the sequences proof. Okay, so this right here makes me say let the big N be 1 over epsilon. And then just to finish the proof, the prestige, if n is bigger than the big N, we have 1 over nx. Well, I guess I should start with minus 0. That doesn't matter. This is equal to 1 over nx. And then this I can say is less than or equal to 1 over n. This is less than 1 over the big N, and this equals epsilon. All right, the old epsilon and big N proof, okay? So this one does converge uniformly. If I were to try to extend the domain all the way over to 0, then the convergence would no longer be uniform. But 0 is not part of the domain, so you wouldn't really do that anyway. All right. Any thoughts about that one? We got about 3 minutes left, but I think I'm going to leave it at that. So next time we'll look at some examples where the convergence is not uniform, but we'll leave that till next time. All right, we do have homework due tomorrow. Check it out.